Hi everyone, nice to meet you. We from Group 5 would like to present our project entitled Project Computational Biology. First of all, this project consists of 5 questions. First question is about hidden Markov model. Second is about distance algorithm. Third is about Bayesian network. The fourth question is principal component analysis (PCA), and last but not least is SVM support vector machine. Let's go to the first question. For the first question, it is about hidden Markov model method (HMM) for gene prediction. And we need to know what is gene finding and prediction in genomic DNA. They have two main problems in gene prediction, which is for the first is the prediction of protein coding regions, and the second is prediction of the functional size of the genes. As we know that the genes having exon, intron, and functional sites, such as coding sequence CDS, untranslated region UTR, and this is very important for us to predict of the protein coding regions and the prediction of the functional size of the genes. What is the advantages of the gene prediction? First, it is able to determine the function of gene and distinguish its product from a functional gene. It also predicts the structural genes, protein-protein interactions, and regulatory system process such as structural genomics, functional genomics, metabolomics, and transcriptomics, proteomics. Again, what is hidden Markov model? Hidden Markov model, or known as HMM, are a ubiquitous tool for modeling time series data, the time corresponding to the position along the DNA sequence. HMM is a generalization of a Markov chain in which each internal state is not directly observable, but produces or emits an observable random output, which is external state, or also called as emission. This is an example of the Markov chain, which is included state, state transition matrix, and initial distribution. HMM used three algorithms to predict the gene, which is first forward algorithm, then Viterbi algorithms, and forward-backward algorithm. Forward algorithm describe how likely for the given sequence. Viterbi algorithm compute the most probable path for generating the given sequence, and for the forward-backward algorithm, it describe how can we learn the HMM parameters given a set of sequences. Application of HMM in gene finding and prediction in genomic DNA. HMM can be applied in gene finding and prediction field. The HMM can be used to predict the structure of the gene and find the coding and non-coding region of an unlabeled string of DNA nucleotides. A gene in DNA nucleotides consists of introns, which is uncoding region, and the exons region, which is coding region. The introns are regions that need to be removed as it will disrupt the transcription process to form the protein sequence. And normally, the introns are longer than the exons. HMM can also be used in modeling grammar as many biological sequence analyses having grammatical structure. The input to the HMM is the genomic DNA sequence, and the output is the parsed tree of exons and introns on the DNA sequence for the simplest case. Let's look to this diagram. Here we can see the intron part and the exon part, which is we can see here the intron part is very long compared to the exon part, and what we need to do here is we need to cut off the intron part by using start codon, codons, and the other sites, and we will doing this cutting process by using HMM, hidden Markov model. How it is applied? This is an example of how gene prediction is applied by using HMM. Here we see that this model are using HMM, which is Viterbi algorithm, to find the most probable path throughout the model, which is in this model, HMM will evaluate the gene, decode and make the model learn about the gene. Hence, it can predict the gene, which is non-coding or coding region. This is example of the flowchart and how the simple transition that shows how HMM works to get the gene prediction. After that, they need to do first transition matrix and second order model for the evaluation of the gene prediction. Criteria of score in evaluating gene prediction methods. Of course, we need to evaluating these gene prediction methods as we need to get the better and accurate result. Comparison of the accuracy and reliability must take into account the following. First, the type of algorithms. Second, the number of sequences used for training and testing. And third, the method used for evaluation, which we would like to cover about this. It is impossible to rank the predictors by only a single measure. Sensitivity and specificity are probably the two most widely used measures in gene prediction. The accuracy of the predictions can be measured at three different levels, which is coding nucleotide sequence, exonic structure, and the protein product level. For the nucleotide level, it measures SN, which is sensitivity, SP, specificity, CC, correlation coefficient, and AC, approximate coefficient, which is it gives an overall sense of how closely the predicted and actual coding regions are in a sequence. But please remember that nucleotide level is not accurately reflects the identification of the precise exon boundaries. And then for the exon level is mainly provides how well the sequence signals such as splice sites, start codon, and stop codon are identified. It is comparing predicted and real exons along the test sequences. And for the protein product level, it comparing the protein product encoded by the actual gene in the test sequence with the protein product encoded by the predicted gene. Then we go to the part of the implementation of HMM method in figure 1 for protein name as SCCY. Look the diagram with me. First of all, as you can see that the number here, the number at the path and the number at the box, which is here 0.4 and here 0.3. The number in the box, which is here 0.3, we have 0.6, 0.5 and so on, indicates the probability that an amino acid occurs in a particular state. And the number next to the directed arcs, for example here, 0.46, shows probabilities which connect the states, connect states between A and C. And then the highlighted path, which is here, 0.4, 0.46, 0.97, 0.015, 0.73 and 1. Okay, the highlighted with the black one shows the probability of A, C, C and Y. As you can see, we have three kind of shape of the box, which is at first we have square part, box part, which is the square part is called mesh states. Okay, all the boxes actually represent the states, and for the box states is represent mesh states. And for the diamond part, which is here, here, and here, and here, it called insert states, which is we want to insert the nucleotide sequence. And then the circle part, which is here, start, here, here, and to the end, is a silent state and known as delete stator and model deletions. This type of, basically if you can see here, this type of HMMs are called profile HMMs. And do you know what algorithm that used in HMM here? For this HMM, it uses forward algorithms. Why I say that it's used for our algorithm? Because it's used to find the probability of the sequence in this HMM model, because it describes how likely for the given sequence. As we look at here, the sequence is already given ACCY, and we can say that it is forward algorithm compared to Vector B that is used to find for the computed probable path, and for the forward backward algorithm is more likely towards parameter of the HMM, which is not included in this diagram. Then I would like to tell to you about steps in computing matrix. After already gone with the HMM, after that we need to computing the matrix. After we already know the states, then we need to computing the matrix. Okay, the step is following here. First, the probability that amino acid A was generated by state IO is computed and enters as the first element of the matrix. This is 0.4 times with 0.3, and we get it as 0.12. And then the probability that C is emitted in state M1 multiplied by the probability of the most likely transition to state M1 from state IO, and in state L1, which is multiplied by the probability of the most likely transition to state 1 from state IO, are entered into the matrix element indices by C and L1 or M1. Then the sum of the two probabilities, which is sum from the L1 and M1, is calculated. After that, the point is set from the winner back to state IO. And then last but not least is step 2, and step 4 are repeated until the matrix is filled. The probability of the sequence is found by summing the probabilities in the last column. I know that it's quite complicated, but don't worry. This is example of the matrix for the forward algorithm, which is, you can see here that what I say just now. For the probability that amino acid A was generated by state IO is computed and enters as the first element of the matrix. This is 0.4 times 0.3. This you can see it here. 0.4 times 0.3 we get is 0.12. And then after that, the probabilities that C emitted in state M1 multiplied by the probability of the most likely transition to state M1 from state IO. And then in state L1 multiplied by the probability of the most likely transition to state L1 from state IO, and enter into the matrix element indices by C. Okay, which is actually, to make it simple, it multiple here L1 and M1. After that, for the second C, which is here 0 and 0.12. After that, Y 0.0001 and 0.002. How all of this is calculated is based on this diagram. Based on this diagram. Okay, for example, this as I said just now, 0.4 times 0.3 is equal to 0.12, and put it here in this matrix 0.12. Okay, to make it you more understandable, let's see most clearly example, which is calculation. Rather than the matrix part, we will show to you the calculation. Okay, this is the calculation of STCCY probability along this path. We are using probability calculation, which is what you need to understand here, and what you need to focus is the highlighted part. Okay, which is here until this part. And then along this part, you need to multiply all of the probabilities. As I said just now, here is also probabilities, and here is also the probabilities. Here is probabilities, which are connect to the states. This is connected states between start states and the states. And then the probability in the box here is about the probability that an amino acid occurs in a particular state. Okay, so looking here, calculate with me. This is 0.4, and then it go here 0.3, so 0.4 times 0.3, and then after that A go to the C state. Okay, so we have two here, 0.46 and 0.6. After that it go to the another C state. which is 0.4497 times for 0.5. After here, you can see it go to the silent state. It doesn't go to the mesh states. It's go to the silent state. And then, so we multiply here 0.015, and here is doesn't have any probabilities. That's the reason why you can see in here is 0. If you can see here, it is a 0 because it is goes directly towards the silent state. And then, so we doesn't need to calculate it. And then after that, after 0.015, then it's go to the Y state, which is the diamond state, which is insert Y, because it's already skipped the C part, isn't it? I mean the box part. So it's time 0.73, and then after that we have 0.01 here, and then towards the end state having one probability, and then times all of this because probability, then we get the answer 1.76 times 10 negative 6, which is 10 power of negative 6. This is all from for HMM. Then we go to the second part, which is distance algorithm.
Next question is question 2, which is biologically relevant distances require algorithms. Hamming distance. What is Hamming distance? Hamming distance is the minimum number of single character substitutions needed to turn one string into the other between two strings of the same length. For example, as you can see in this example, string 1 and string 2, you can see that the yellow highlighted letters are the characters that are not the same, not equal. So we can conclude that the Hamming distance in this example is equals to 4, since there are 4 letters that are not equal between these two strings. So the importance of Hamming distance in sequence alignment is that to count the mismatches between the sequence. If the sequence are not of equal length, then use the Levenshtein distance, or also known as the edit distance. Secondly, it measures the dissimilarity between two sequences. For example, the number of positions at which the corresponding character are different. And third, to count the mismatches between the sequence. If the sequences are not of equal length, then use the Levenshtein distance, as I've mentioned just now. It is also known as the edit distance. There are three limitations of Hamming distance approach in sequence alignment. Firstly, the two sequences having high similarity might fail to align. Secondly, we cannot perform edit operation on any sequences by using Hamming distance. And thirdly, we cannot calculate the distance between two sequences of different lengths. So for the second question, we can conclude that Hamming distance finds the minimum number of substitutions between a pair of sequence, which, in other words, number of substitutions needed to transform one sequence into another, and that Hamming distance can only be used for sequences of the same length. Okay, next is question 3, which is the Bayesian network is one of the important algorithms in computational biology. Okay, Bayesian networks is a type of probabilistic graphical model that is used to build model from data of probability distribution and wide range of tasks such as prediction, anomaly detection, diagnostic, and decision making under uncertainty. Also known as Bayes nets, belief networks, probabilistic networks, and causal networks. Graph that made up of nodes and links. Bayesian networks is a directed acyclic graph, which is consists of nodes that represent variables and links that represent dependency of relations. DAG is used to represent causal relationship among a set of random variables. Two main approaches to search for Bayesian network models are PC algorithms that perform a series of tests on conditional independence of sample, and the result will be used to construct the set of DAGs that closely implies the test result. Next is the assigning a score to each DAG based on the sample data and searches for DAG highest score. Bayesian network structure is a learning research that focuses on learning the dependency graph for one problem in isolation, also known as the statistical task of model choice, where the candidate statistical structural models are ascribed to as a cyclic directed graph. Uses the score and search approach for maximization of a quality criterion Q. Q is known as a score or a scoring function that the real function of the acyclic directed graph G and the observer database D. There are two major approaches of network structure learning, which is score-based approach and constraint-based approach. Next is the discretization of Bayesian network. There are three commonly used discretization methods, which is the equal interval, equal quantile or equal frequency, and moment matching. Equal interval is when the data is divided into equal length intervals. It is either for roughly uniform data distribution, but it will be problematic if distribution is not uniform or with the presence of the outliers. Besides that, for the equal quantile, it divides data into groups of equal sample size, and it is designed to capture one or more concentrated modes distribution. For moment matching, it matches the moment of discretization distribution with moments of continuous data. It is designed to capture data distribution in a systematic way. So, in conclusion, the moment of discretization distribution is equal to the moment of the continuous data. The rules that represented decision tree is the first one shows that the decision tree contains one child variable that is binary target D and two parent variables which are also called the predictor variables gene A and gene B. Next is the BRL Global Structure Search, which is known as BRL-GSS, with the Conditional Probability Table (CPT) represented as decision tree with global constraint. And lastly is the decision tree that shows the decision tree represented as rule-based. It contains a conjunction of predictor variable assignment as shown in the path of the decision tree.
Alright, for question 4, we discuss about principal component analysis. PCA is one of the feature extraction method for high dimensional data. Principal component analysis (PCA) is one of the feature extraction method for high dimensional data. The purpose of PCA is to distinguish different category in a dataset. It can be applied to low dimensional space as long as there is still different attribute in the data. PCA should work on the data. E-evolves is one of the E-game decomposition component which determine the magnitude. Bar EXP explain variance tell us how much information variance can be attributed to each of the principal components. Bar EXP represent the cumulative of the explained variance. Explain PCA plot. PCA plot is a proportion of the variability in the data that each principal component explains. The higher the proportion, the more variability that the principal component explains. Based on the figure, first component 70% approximately, while the second component shows 20% variance approximately. At the, and the last principal component may not be important enough to include it since it only shows less than 10% variance only. On the last question, describe about advantage by applying PCA for gene expression data. PCA for gene expression data suitable for datasets for large experiments like the gene expression, which have different dimensions in dataset. PCA is recommended as an exploratory tool to uncover unknown trends in the data. And lastly, PCA used on gene give way to identify predominant gene expression pattern.
So the last question for this task is question 5, which is support vector machine SVM robustness and scikit-learning in Python. So support vector machine. It is a non-probabilistic binary linear classifier. It is based on the concept of decision planes that define decision boundaries in which that the plane that separates between a set of objects having different class memberships. Support vectors are the term used to describe the data subset that supports the decision boundary, whereby if it is removed, would change the position of the dividing hyperplane. It is considered to be the important element of a dataset. The figure on the right is shows the definition of support vector machine for better understanding of for support vector machine. SVM robustness to outliers. Support vector machine SVM is a highly successful machine learning that is commonly used as a classification method in real-world data analysis. One of the limitations of SVM is that it is not very robust to outliers. The presence of a few outliers can lead to a very bad global misclassification, especially in the accuracy measure of SVM. Thus, for this reason, an outlier detection is very much needed to tackle this limitation of SVM, and that researchers have been finding out ways to improve the robustness of SVM against the outliers. SVM robustness to outliers. A method to detect outliers have been proposed by researcher named Wang in 2006. It is called the SVM outlier detection (SVMOD). The proposed method aims to increase the robustness of SVM to outliers by solving the VSVM, a method developed by Shkolkov et al. In 2001. The study have proven that SVM-OD is able to detect outliers as compared to VSVM as it avoids the penalty factor V, which is required in VSVM. The experiment conducted on synthetic dataset also shows that when the kernel parameter C parameter is fixed, SVM-OD can detect some local outliers while the VSVM cannot do so. The role of C parameter tuning in increasing SVM robustness. The C parameter is the regularization parameter in SVM training. It is quantitatively robust towards a fixed regularization parameter. Lowering the C parameter, which is the regularizing parameter, into an optimum value can increase the robustness of SVM towards the outliers.
Next, we will talk about robust and not robust outliers. Okay, the characteristic of robust to outliers is that it throws away information that contain noise and signal, while in not robust to outliers, it cannot detect local outliers as data is full of noises. Next, robust to outliers protect from irrelevant and misleading information, while for not robust to outliers, it is easily affected by the errors present in the data. Besides that, robust inputs can be tricky as they can be quite coarse in distribution of values and have relatively small number of integer values. While for not robust to outliers, the real data has incorrect values which will disturb the final result of the algorithm. Okay, Some example of robust estimators is the least median and robust regression that is used in SVM. For not robust to outliers, the example of not robust estimators are standard deviation and regression.
Hello, now we go to the three parameters in SVM. Actually, SVM have so many type of parameters, but in this project, we only focus on three parameters, which is epsilon parameter, C parameter, and gamma parameter in SVM. The C parameter is the regulation parameter of the error term, which is it controls the trade-off between errors of the SVM on training data versus model complexity and margin maximization, which is C equal to infinity leads to hard margin SVM. It trades off misclassification of training, example against simplicity of the decision surface. A small value of C will resulting in increasing the number of training error in SVM, while the large value of C will lead to such behavior that's similar to hard margin SVM, or aims for classifying all training examples correctly. Apart from that, the C parameter also controls the trade-off between the margin and the size of the select variables. To make it simple, the C parameters have been responsible for the error term in SVM, which is if we want to minimize the error in our SVM, so we need to check out our C parameter. And then for the epsilon parameter, it will determine the level of accuracy of the approximative function. It will affect the smoothness of the SVM's response, and it affects the number of support vectors. So both the complexity and the generalization capability of the network depends on its value. A large value of E can be utilized for a very noisy training set. So E parameter is basically more toward accuracy of the SVM. So if you want to have more accuracy, so you need to adjust for the epsilon parameter. And then last but not least is the gamma parameter. Gamma parameter defines how far the influence of a single training example reaches, with low value meaning far and high values meaning close. The gamma parameter can be seen as the inverse of the radius of influence of sample selected by the model or supervectors. If gamma is too large, the radius of the area of influence of the support vectors only includes the support vector itself, and no amount of regularization with C will be able to prevent overfitting. The gamma parameter basically is about the dataset itself, which is about the radius of the area of influences towards the SVM, which is we need to get for the data result, you need to adjust it. Low values meaning it will very far with the example reaches will to reach what we want, and for a high value meaning closed.
Last part of question 5, we'll explain about tuning parameter in SVM. SVM have a few parameters that have been tuned to get a better performance. For example, parameter gamma and parameter C. The gamma value responsible for linearity degree for the hyperlink, thus it has to be tuned to be better fit the hyperlink to the data. Due to hypothesis result, the smaller gamma value, the more hyperlink is going to like a straight line. Otherwise, for parameter C result, the smaller the value of C, the greater the submerging. Thus, it means that point inside this submerging are not classified as any of the two categories. Thus, the greater value of C might lead to be better result. As a consequence, for both parameter, the small value will induce the better result for SVM performance in classification.
This is skit-learn machine learning in Python, which is if you want to learn more about machine learning in Python, you can go to the skit-learn website. Okay, this is the overview of the machine learning tasks, applications, and algorithms of the skit-learn machine learning in Python, which is In this website, machine learning task is divided into seeds, which is we have classification, regression, clustering, dimensionality, reduction, model selection, and pre-processing. Okay, let's go through one by one. For the classification task, the application is about kind of spam detection, image recognition. And the algorithm that is used is SVM, suborbital machine, nearest neighbors, and also random forest. And then for the regression task, the application is about drug response and the stock prices. Algorithm is SVR, rich regression, and lasso. And then clustering, the application is about customer segmentation, group experiment outcome, and the algorithm is k-means, spectral clustering, and also mean shift. For the dimensionality reduction, the application is visualization and increase the efficiency. The algorithms is PCA, principal component analysis, feature selection, non-negative matrix factorization. For the model selection task, application is remove noise from images, sequential prediction. Algorithm is model selection algorithm, a fixed point image denoising algorithm. And last but not least is a pre-processing. The application is transforming input data such as stats for use with machine learning algorithms. And the algorithm is random forest.
So to conclude question 5, we can conclude that there is a close relation between the robustness of SVM towards outliers and its parameter tuning. Secondly, a particular parameter value increase, which in this case is the C parameter. It will increase the robustness of SVM towards the outliers. The last part is the scikit-learn, which indicates that a particular task can be applied in many types of applications, and that there are a variety of machine learning algorithms that can be deployed and their performance on a task can be compared. So that's all from us. Thank you.